In progress.
All right. So good news, my jury duty ended a little early, so I'm able to come back and teach. I was and Dr. Patterson is one of the best, so I'm very excited that she was able to come in and go over Lewis dot structures with you. I think happy Friday. I kind of don't want to start 3.6 today. So if you don't mind, I'm going to finish up Lewis dot structures today and then give you the rest of the day off. And then we'll come back on Monday and start Vesper or VESPR. So yeah, I was watching the video from Wednesday and y'all ended last class on formaldehyde. It's a little tricky, but I saw that y'all were able to finish it. And then today I would like to start with nitrogen. If you are rusty with Lewis dot structures, I think previously there was a slide. Here it is. The procedure for Lewis dot structures. This is a great kind of help me or start guide when you're doing it for yourself. Eventually, you'll get to a point where like you'll have this in your head and you don't need the how to. But while you're learning Lewis dot structures, if you can have like your own little cheat sheet, or you can use this as a cheat sheet to how you get started. So the way that I always get started is count count the valence electrons. So Dr. Patterson mentioned last class that it's just the last digit in the periodic table of elements column number. I love how that kind of conveniently works out. Um, so if I was to look at nitrogen, so question, if you want to put it in the chat, if I was to say nitrogen, what is it? Is it just N or is it N2? If you don't want to do chat, you can always unmute yourself and say something. That's fine. So is nitrogen N or N2?
Wouldn't it just be N?
So nitrogen happens to be one of those Brinkelhoffs. It does not exist by itself. So that's just me kind of testing you on like what we kind of learned in unit 1. No worries. But if I was to kind of like spell it out like this, I would hope that you kind of remember the Brinkelhoff because nitrogen uh, wants to be a diatom by itself. So it would not exist because if it was just nitrogen by itself, the Lewis dot structure would just be nitrogen with 8 electrons around it. And that's just, unfortunately, a little bit too simple. So we have to be a little bit more complicated while we're learning this. But when I say nitrogen, I want you to get comfortable thinking nitrogen is N2. And the valence electrons. So nitrogen is in column 15. And so the valence electrons for each nitrogen would be 5. There are 2, which means the total number of valence electrons is 10. So that's the first step that you always do when you are trying to create Lewis dot structures. So, and remember that electrons are negatively charged. So you can write valence electrons, or you could just do E minus. So that means that in total, I need 10 electrons around these nitrogens. There's only 2, so I don't really need to think about which one's the central atom here because there's just 2. So it's just a nitrogen and a nitrogen. Much more simple than the previous slide for the formaldehyde. Now we need to add electrons around the nitrogens, but I want to make sure I'm sticking to my 10 because if I was to overdo it, that might mess me up. So I'll start with them in the middle. So that's 2, 4, 6, 8, and 10. I kind of I'm tempted to finish the octet and, add until there's enough electrons to go completely around them so each of them have 8. But unfortunately, it does not say I have 14 valence electrons. It says I have only 10. And so I cannot include 14 just because I want to make sure they have a full octet. So just by looking at them, I can tell that each of these nitrogens, the way that I just drew it, do not have that full octet. So the way this is drawn, this nitrogen has 6, and this nitrogen has 6. So I won't say exactly something's wrong. There's always going to be a possibility of things, but where is nitrogen going to be most comfortable? That is our goal here. So according to the procedure, if the octets are not full, you can take from an outer, so lone pair from an outer one and move it as a double bond or a triple bond. So I'm going to start by taking two of those electrons from one of the nitrogen and moving it to the middle, hopefully trying to make, a better full octet for both of them. So if I do that, my left nitrogen now has 6. My right nitrogen also, wait, sorry, 2, 4, 6, yes. And my right one has 8. Do y'all see that? So left has 6, right has 8. So on the right side, I have, a happy full octet, but my left side does not. So for me to complete this, if I want to have both of them have that full octet, I can take this second pair of lone pairs, electrons, and move it to the middle. Okay. So on the left, this nitrogen has a full octet because 2, 4, 6, 8. And my right nitrogen has a full octet, 2, 4, 6, 8. So this one, it seems like it'd be a lot easier, but you want to try to do your absolute best to make them the most comfortable. So your goal is to get full octets. Sorry. So that's going to be where you have to start playing around and moving those electrons around to get the atoms to be as happy as possible. This, if I was to take out those lone pairs and, do it with a triple bond, that's when you have the triple line here. I do have some slides. We'll take these and we'll move them into line drawings, but these are synonymous. So either 6 electrons or the triple line. Any questions on that before we move on? If I was to ask you to do a Lewis dot structure for any of the Brinkelhoffs, so let's review the Brinkelhoffs. That's going to be hydrogen, any of the halogens like chlorine, iodine, bromine, fluorine. All of those will have, so I can put fluorine, and then you have to remember it's F2. Nitrogen, oxygen, those are the Brinkelhoffs. So I can say oxygen right here, and you'd have to create a Lewis dot structure, but the hard part is remembering it's O2, not just O by itself. If at any point you have questions, throw them in the chat. I have it in front of me. Does anyone remember what the chemical formula of nitrate is? Yes, Logan, it is NO3 and the charge is a -1. And you could do a minus like that, or you can do a -1. We still have to follow the same procedure. I will say this kind of throws a kink into things, but I'll show you how to incorporate that in. So kind of ignore that negative sign right now. Let's just do the same procedure as before. Let's count those valence electrons. So nitrogen, I'll try to use the process Dr. Patterson was doing, where you take the first number is the subscript, and the second number is the valence. So nitrogen is on column 15. The valence electrons are 5. So a little do a squiggly for nitrogen. And then oxygen is in column 16. And so it will have 6 valence electrons, and there are 3 of them. Okay. All right. So we are counting electrons here. If I was to have it be neutral, just NO3 by itself with no charge, we are done. But that sign or charge kind of tells us, do I have an extra electron or do I have less electrons? So because electrons are negatively charged and it's negative, this whole ion is negative, it means there is an additional electron here. If it was a positive charge, it would have less electrons. So if I have just a -1 charge, I have to add a 1 because I have one extra electron because it has that -1 charge. If it was a 2-, you'd have to add 2. If it was 3-, you'd have to add 3. If it was like a +1, you would have to take out 1. So that sign tells us, is it extra electrons or less electrons? So this will be a +1 for that, of course, negative charge, adding that extra electrons. So if you add all of this up, 1 times 5 is 5, plus 18, plus 1, I get a total of 24 valence electrons. You'll notice that it should always end up being a neutral, or sorry, not neutral, a even number. It is possible to have odd numbers, and I'll show you, but most of the time between us, it ends up being a even number because electrons want to be in pairs. All right, can anyone tell me what you think the central atom is? So let's review. The central atom will be the least electronegative. So I would say fluorine is the most electronegative, and as you go away from fluorine, both down and left, the less electronegative. So oxygen is to the right of nitrogen. So nitrogen is slightly less electronegative than oxygen. And you'll sometimes also see that we'll put the central atom written out first. It's a trend that we'll do. So nitrogen by itself, and then it's going to be surrounded by oxygen. So 1, nitrogen's written out front, so it kind of gives us a hint that nitrogen is our central atom. And then 2, nitrogen is less electronegative. So I'm going to write it out with nitrogen, and it doesn't matter where you put those oxygens right now. We're trying to figure things out. So I'll put them, you can put them here, you can put the oxygen underneath. It doesn't matter as long as you have those 3 oxygens surrounding the nitrogen. Okay. So we need to add electrons here until we have filled, 24. So I'll start around the central atom. That's 6 here. 8, 10, 12, 14, 16, 18, 22, 24. I can't keep adding to fill the octet. That's not how this works. I have to add the electrons, and if I run out of electrons, I have to figure things out after that. But just add until you hit your valence electrons limit. So I have 24, and if I look here, the central nitrogen does not have a complete octet, and it looks like, wait, let me double check my counting. I might be wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, yeah, that makes no sense. 24. Double check me if I'm wrong, but I'm pretty sure now it's good. So that's 8, 8, and 8. Yeah, sorry about that. But you saw I was able to fix my mistake. I was like, it just didn't look right. It didn't feel right. And I needed to double check my counting. All right, so right now, the way it's written, all of those oxygens have full octets, but the nitrogen does not. So it really doesn't matter which oxygen we pick from, but if I take one of those lone pairs and move it to make a double bond, I will now have nitrogen having a full octet. So once again, if you wanted to pick these two, it doesn't matter as long as you pick one oxygen. And it would look something like that, where this oxygen has a full octet, the nitrogen has a full octet, and each of the other oxygens have a full octet. I'll take this out while you're writing if you are taking notes. I also want to point out that if you have to do a Lewis dot structure for this, you would essentially have to kind of pick and choose which oxygen it would come from. And since all three oxygens could have that double bond, you'd actually have to write this Lewis dot structure out 3 times, showing each of those oxygen having the double bond. It's on the next slide and I'll show you. But one more thing, if you have a negative charge or any charge, you have to put brackets around the entire thing, the entire Lewis dot structure, and put the charge in the top right corner. So it just lets us know that it has that charge. Are there any questions before I move on? So just reviewing what we did on the previous slide, charge does affect the valence electrons. If the charge is negative, you will add electrons to the valence electron count, depending on what that charge is, whether it's a -1, -2, -3. If it's a positive charge, you would remove electrons. So you'd count it up like you normally would, and then you'd subtract however that charge is. Because negative means additional electrons, positive means you've removed electrons. When it is charged, you will put the Lewis structure of an ion in square brackets and write the charge outside of the brackets in the top right corner, just like we did on the previous slide. So I have this is a bracket, and this is a charge. So sometimes, like on the previous, some Lewis dot structures, there can be multiple ones of them, depending on if, you need to move the double bond around because it could pick any oxygen. So equivalent Lewis dot structures for a compound or polyatomic compound that differ only in the placement of the double bond because there's multiple options, they would have something that we call a resonance structure. So the Lewis dot structures do not adequately represent the bonding in these species because it could be any of them. The resonance hybrid is a mixture of these resonance structures, and it is closer to the real molecular ion. That's because there's a delocalization of electrons and molecular orbital theory is needed. So I know that's a mouthful, but I think it's better for me to show you on the next slide. I just want to point out that if there is those two, let me write out the Lewis dot structure that we already had. We had nitrogen, O, O. So up until now, we've really been doing Lewis dot structures where we have the dots instead of bonds. But Lewis dot structures can be drawn two different ways. You can have all of the Lewis dots in there, but eventually you might start shorthanding it a little bit where instead of having the 4 dots to represent the double bond, I would take that out and just draw out the double bond. So if I saw one line, I would have to recognize, okay, there's 2 electrons in that one bond. If there's a double bond, there are 4 electrons. So it's the same thing as drawing it out with the dots or drawing out with the lines. So it depends on what you're comfortable with, but either of them are correct Lewis dot structures. So previously, I think this is the one that we drew here, but that double bond could go to any of those oxygens. So the correct way to draw the Lewis dot structure of something that can have multiple or a resonance structure is you would draw it out each way. So have that double bond on each of those oxygen. And then what you do is you put the brackets around it like so. And then you do the charge. And then this just tells you, this little double-sided arrow just tells you like, this can be a Lewis structure, this can be a Lewis structure. So it's kind of just telling the reader, myself, that like this is a resonance structure, meaning that those double bonds can shift and there are different options. So if you do see that, make sure you put the brackets with the charge, and then you would just do a double-sided arrow to let us know that, okay, now the double bonds on this oxygen, now the double bonds on this oxygen. Yeah, okay, so here is the resonance structure. So previously on the previous slide, it mentioned that there's a hybrid. So what happens deep down, it's just harder for us to draw. It's better to draw all the options out here. But if we were to like be doing a lot or more research on this, they would actually find that the single and double bonds, since it can be on any of those oxygen, it kind of creates this hybrid beauty of, let me show you what I mean, sorry. Let me get a different color. Nitrogen, oxygen, oxygen, oxygen. So, oops, sorry. So because that double bond could be any of the on any of those oxygens, what happens is it delocalizes and it kind of creates a hybrid compound where the double bond's kind of between two of those oxygens. So it's kind of like happening where it could be between this one or this one. But when we're learning resonance structures, it's just better to draw out all three versus having to create this weird hybrid structure. So yes, deep down, it would look something more like this, where the double bonds between two of those oxygen, but it's just simpler and better to draw out all three. So this would not be an answer option for an exam. You might be asked, hybrid, but you wouldn't be asked to draw it out. So if you were asked to do that Lewis dot structure, you would have to draw it out like this with the resonance. And I have another example for us to practice. This is carbonate. Does anyone remember what the compound of carbonate is and the charge? So there's definitely carbon in there.
Would it be CO3 too?
Say it again.
Would it be 3, 2,
CO3.
and then a 2?
Yes, it would be a 2 minus. Perfect. All right, let's count the valence electrons. So carbon, there's one carbon, and each of those carbons will have 4 valence because it's on column 14. And it has a -2 charge. So do I add or remove electrons? You have to add because you're adding additional valence. So here would be +2. This compound would also have 24 valence electrons. what is the central atom? Yes, so once again, we tend to kind of write our central atoms out front. And two, carbon is not as electronegative as oxygen. So carbon will be the central atom for carbonate. So this compound is going to look very similar to nitrate. I still need to have all of my electrons on there. There's 24. So I think we would just put 8 around each oxygen. And that would be a great starting point. So if I count again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So yes, this is 24 valence electrons. Can anyone tell me, is it done? Is this correct? So before you say yes or no, the best way you kind of want to look at everything is you want to count and make sure each atom has a full octet, with the exception of hydrogen, who does not carry 8, it can have 2. So if I focus on each of those oxygen, yes, they all have full octets. So the oxygen are very happy, but look at carbon. Does carbon have a full octet? So our goal is to make these atoms as happy as possible. We want everything to have a full octet if we can give it to them. And I'm going to give you all a hint. When you get up to organic 1, if you are going to go that far into chemistry, carbon always, always wants a full octet. Everything else can kind of suck it up, but carbon always wants to have, remember we talked about those alkanes? It always wants to have 4 bonds or have four things attached to it. So carbon is one of the most, I would say, selfish, because it doesn't want to have that full octet. So it doesn't matter what oxygen you pull from, because it could be any of them. All of them could do this. But I'm going to start with 1. And I'm going to move that lone pair to create a double bond. And then by doing that, I now will have a full octet with carbon. So let me just erase this real quick. I'm going to just fix that. So I moved it here. Okay. Now if I check each of those oxygen, so this oxygen has a full octet. This oxygen has a full octet. This oxygen has a full octet. And most importantly, the carbon now has a full octet. So this one we can stop, and let's complete the drawing. You put the brackets around it, and you'd say the charge. So this one, it's not completely complete because it is a resonance structure, but at least now we have a correct Lewis dot structure. It's as correct as it can be. The way that we would complete the Lewis dot structure is finishing the resonance structure. So I would have to redraw this Lewis dot structure, but move the double bond to every oxygen available. So I'll do that right now. So So I put the double bond, I had the second pair of electrons in red. So you can see how I'm shifting the double bond to every oxygen it could go to. If it's a resident structure and there are multiple possibilities, you have to show everything. So you have 3 oxygens here. Each of those oxygen can have a double bond. And so I need to have 3 residence structures for this Lewis dot structure to be correct. If there's only one possibility because there's one oxygen, like y'all did with formaldehyde, then you don't have to draw multiples. But typically when you have ions, they tend to have multiple Lewis structure possibilities. Okay, so for the next several slides, I also want us to practice the other way of drawing Lewis dot structures. So I'm going to take what we've already done in last class and this class, and instead of us doing the dots for the bonds, I'm going to just take out the dots and replace them with lines, because I want us to practice both ways. So on the next slide, I have carbonate again, but I want us to practice drawing it with the lines. So carbon, oxygen, oxygen, oxygen. So it had 24 valence electrons. So you always want to start by putting a bond between the central atom and everything connected to it. So instead of me doing dots, I would just draw a bond. And I have to recognize that every time I see a line, that line represents 2 electrons. I'm doing the same method as before. I'm adding electrons onto this until I have filled the 24 valence electrons. So it's the same concept as the previous slide. I'm just keeping the lines in there. So if I was to count, this is 2 electrons. So around the carbon, there are 6 bonds. So, sorry, 3 bonds. So 6 electrons total. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I can still count and say I have 24 valence electrons. And I can also recognize around the central carbon, the way this is drawn, there is not a full octet. So that is not a full octet. That's 6 electrons. So I would need to take one of those oxygen to donate its lone pair to make a double bond. So we just did the same thing on this slide that we did the last slide, but I'm just kind of making it a little bit cleaner and replacing the bonds with, or the lone pairs with bonds if they are connected between 2 elements. So you still want to count 2, 4, 6, 8. So the carbon now has 8 around it, so it has a full octet. So the oxygen here is 2, 4, 6, 8. Oxygen has a full octet, and then these oxygens have full octets. So I'm going to count my electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 20, 22, 24. So it does have all 24 valence electrons drawn here. You want to be able to do line drawings, and you also want to be able to do with just the dots themselves. But I kind of want to complete this because you know, this is not a complete resonance structure. We need to make it look like here where we have all three versions. So I'm going to go and repeat this with all three versions. All right, so let's continue practicing Lewis dot structures with this other method. So I just copied and pasted the previous slides. So methane. CH4, same process, count those valence electrons. Carbon will be the central atom because hydrogen will never be the central atom. So I need to have all of those hydrogens around the central atom. But instead of me starting with dots, I'm just going to do a line. And if I count that line as 2 electrons, I have 2, 4, 6, 8. I have my total amount of valence electrons. My carbon is very happy because it has, it has a full octet. And the hydrogen has its full, I guess, duet, because there's 2 of them. So this is how you can draw methane, which you've probably seen before when we did alkanes with the line drawing. So this, even though you don't see any dots, is also correct. This is the correct Lewis dot structure if you were to have just those bonds. Does that make sense? Question, would this one have a resonance structure? Would this one have multiple versions? No. So this one, yeah, we're done. That's it. Okay. Carbon tetrafluoride. So same process, count those valence electrons. Let me just double check my math. Yeah. So just like the previous one, fluoride is the most, or fluorine is the most electronegative. So carbon is definitely not as electronegative as fluorine, and carbon's kind of written out front. So it tells us carbon's probably going to be the central atom here. So I will do the same. And I will put all 4 fluorines around the carbon, and then always start by attaching a single bond. Always start by doing that. Don't try to do double bonds until you have all of the valence electrons. So I have 4 bonds, so that means 8 electrons. I will count until I have 32. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's it. Now I have to check and make sure everything has a full octet. And then if it does, I'm done. So, does the central carbon have a full octet? Okay, carbon's done. Does each of these fluorides have a full octet? Yes. So we're done. We don't have to draw this any further. And I mean, this is the correct Lewis dot structure for carbon tetrafluoride if you were to do bonds. So once again, if you were asked to do the Lewis dot structure, you don't have to kind of pick and say, this is the more right one. You can do either of them. But if I was to draw one or the other, it's important to be able to distinguish between both of them. Both of these are valid, both of these are correct, and both of these are considered correct Lewis dot structures. Formaldehyde, that was the last one that y'all did last class. So that would be, say, 1 times 4. Four plus 2, 6 plus. I know that y'all already did this last class, so I'm kind of going a lot faster through this instead of, slowing it down like y'all did with Dr. Patterson. But carbon will be the central atom. It is the least electronegative, and then hydrogen is less electronegative, but it's never the central atom. But carbon is not as electronegative as oxygen. So this would be the setup. So once you have your central atom drawn with all of the attachments, the first thing you do, once again, is draw the bonds between them. Start with a single bond. Okay. Once you have all your single bonds, you add lone pairs until you hit your limit of 12 valence electrons. So I can't add lone pairs to hydrogen because these hydrogens already have their max capacity too. The only place that I can add those lone pairs is to oxygen. So 2, 4, 6, 8, 10, 12. Are we done? Is this correct? So check if it's correct or not by counting and making sure every atom has its full octet. Hydrogen, oxygen all have full octets or duets. Does carbon have a full octet? No, carbon has 6, not 8. So the first thing we have to do is take one of those lone pairs from the oxygen and make a double bond. So I'm going to, I guess I'll put an arrow here. And now all of my atoms have a full octet. So yeah, it just depends on what you're more comfortable doing. I personally prefer to do this method over having dots because as you can tell, I'm not very good at drawing dots. I'm not the best at it. My dots are very messy, so that's why I tend to draw bonds instead of a bunch of dots. I do my best though. Nitrogen. So like I said, we've already done this compound, but I would prefer to redo it where we're doing bonds instead of dots when things are connected. So that was N2. So 2 times 5. So there is no central atom. So, but I have to connect whatever I have in front of me with at least a line. Okay. So I have 10. So that's going to be 2, 4, 6, 8, 10. Okay. I can't add any more because now that would be 14 and it wouldn't be correct and it would throw off everything. So I can only add 10. But so this nitrogen has 6, this nitrogen has 6. So we can't leave it like that. We have to help out and make these nitrogens have full octets. So to do that, I have to add lone pairs to the middle until I do. All right, so by adding 1 lone pair, this nitrogen has 6. This nitrogen has 8, so it's not quite there yet. So now each of those nitrogen have 8 valent or 8 to fill its octet. And if I was to count the total number of electrons, we have 2 electrons here, 2 electrons here. That's 2, 4, 6, 8, 10. So now we have our 10 valence electrons. And everything has its full octet. So this would be the Lewis dot structure for N2. Does anyone need or have a question about using this different type of way of doing it? Does anyone have questions or need me to go back and slow down or clarify? Okay. So it's about to be 12:50. So let's just come back. Let's have our mental break and come back at 12:55. If you haven't downloaded the worksheet, so the Lewis structure worksheet that I have on under modules, so go ahead and download this because we are going to do this and maybe get some answers in before you go. So download this during this break and then we'll come back in 5 minutes.
Recording in progress.
Okay, so let's continue. There are going to be some exceptions to the rules. The biggest exception, of course, is hydrogen. Hydrogen cannot have a full octet. So it will only max out at 2 electrons, but other elements similar to hydrogen will be in the same boat. For example, beryllium. Beryllium is column 2, but it just doesn't have a lot of valence electrons. It only has 2 valence electrons. So it's kind of similar to hydrogen where it can act as that central atom, but it can't have more than 2 bonds connected to it. So 4 atoms in total around it. Yeah, 2, 4, yeah. So beryllium is an exception to the full octet rule. It's very happy having its 2 bonds or 4 around it. Boron is another one. So boron has 3 valence electrons and it can max out at 3. It doesn't want to have that full octet. So those are those kind of unique ones where you don't want to force those to have more electrons than they can, but the good news is it just won't happen. Like you'll count the valence and then you just have to remember, okay, these are happy not having their full octet. And that just takes practice. I do want to point out that it is possible to have odd number of electrons. Radicals are what we call them. It's very rare because they're very unstable. So yes, you might be asked to draw it. This middle one here shows that odd, uneven number. And yes, there's a possibility of everything. It's just not going to happen as much as the evens. And that's because radicals are very unstable. It is also possible for an atom to have more than 8 electrons surrounding it. And these are also exceptions to the rule. So elements on the third row of the table and below, so bigger elements. So things like beryllium and boron, they're very, very small, low atomic numbers. So they're happy having less or up to 8. But elements in the third row and down, so third, fourth, fifth, sixth, seventh row, they can actually have extended, have more than 8 in their octet. So that's because sometimes you can start adding more than 4 bonds to it. And if you have more than 4 bonds, it just keeps, every bond is 2 additional. That's because these elements or atoms have large enough orbitals around them to accommodate more than 4 bonds. And then sometimes you'll have access to d orbitals. So with the previous explanation there, but these are, so like I said, I would say third row that starts with aluminum, silicon, and phosphorus. So anything after that can have more than 8 under certain circumstances. And I'll show you that on the next slide. So we have sulfur. Ooh, how about this? Can y'all remember how to name this? Yes. So this is a binary covalent compound. So it's going to go through those rules. So we don't do monosulfur. It just does sulfur. And then there are 6 fluorides. So it would be hexafluoride. So I could write SF6 or I can say sulfur hexafluoride. You have to be able to draw it out. It doesn't change how we do Lewis dot structures. It just doesn't. So you start with the valence. Sulfur is on row 6. Fluoride is on, I'm sorry, not row, column 16. So that's 6 valence. Fluoride is in column 17. So 7 valence. So 48 valence electrons. Question: what is your central atom? Yes, sulfur is going to be your central atom because it's written out front and it's less electronegative than fluorine. So S, and then I have to draw out all of the fluorines around the central atom. You can't assume that the fluorine's attached to other fluorines. It's not going to be like, that's not what we're doing here. So you have to identify your central atom and put all of everything around the central atom. So let's do F, 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 F. That's 1, 2, 3. Yeah, that's 6 fluorides around the central atom. So I'm going to do this both ways. I'll do it with the previous way you discussed with Dr. Patterson, and then I'll show you with the lines. Or how about I do that now? Okay, so we'll do it both ways here. The next step is you want to connect those atoms to the central by either doing a line or doing the lone pairs. That's 2, 4, 6, 8, 10, 12. So now I have to add up, or keep adding electrons because we're finished with sulfur, but we can add them to the fluoride. So until I've hit my 48 total electrons. So I'm at 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. I'll do it together, 1, 2. So I have my total valence electrons on each of these. And if I look at those fluorines, all of those fluorines have a full octet. The only thing that does not have a full octet is sulfur. But sulfur doesn't have under the recommended eight electrons. It has over. So as long as I hit everything that it's asked for, and sulfur is on the third row, so it can accommodate a extended octet. So this is the correct Lewis dot structure for SF6. Either of these drawings are correct. Any questions on this? If you do, please ask them, but right now I'm going to switch over to our worksheet. So I do want to point out this worksheet is for us to kind of do over 2 days. So I only want you to do the Lewis dot structure for the compound in the Lewis dot structure. Also, let me put this up in front of you. Might be easier to kind of highlight what I'm talking about. Let me switch over to the dot cam. Okay, so here's that worksheet. I only want you doing the left column. So we will do this column at a later date. So I only want you doing the Lewis structure. And then I know it says number of electrons here, but just assume that's number of valence electrons, okay? So I know it's really bright, but that's CO2. So CO2 and just do the left-hand side. And if you keep going, all I did was just keep adding more and more. So we're gonna go ahead and practice this for, I guess, the rest of class. But once, I guess, we can come back in a little bit and maybe do a couple of them if you have questions on any of them, but I highly recommend working on this worksheet for like the next 15 minutes. The key is available and online right now if you need additional help.